So you see, you're seeing real time, you're seeing it live, what's going on right here. We are testing just the output, right? And from the results of the test, it's hard to tell where exactly things went wrong. Hey, welcome back. So if you watch my previous video, we extracted the core capability out of the spreadsheet and tried to implement it using TypeScript. But then I realized that's out of order. Why? Because first we need to know whether or not we're successful with the extraction itself. And how do we do that? By writing a validation test. However, I remember we did not discuss any explicit form of validation or verification for this particular exercise. But if we pay close attention, we can imply the acceptance criteria around that validation. What is it exactly? We just want to know, we need to know that we extracted the capability properly, successfully. How? Simply by comparing the outputs from the spreadsheet. Well, you might say, it's not a proper validation. Well, in this case, it would do. And then, in succeeding videos, we would formally verify this on actual ACI examples, references, manuals, etc. But the point now is we need to know first whether we're successful in extracting the same capability by comparing the spreadsheet and our output. So that's how we do the validation test. All right, so as I was saying, we just need to know whether we're successful in extracting the core capability by comparing the outputs from the spreadsheet. And so I have here an interface to represent the output that we're interested in. So let's take a slice of this segment, these two 16s. So the interface you're seeing right here, neutral axis, depth, axial force, and moment, correspond to these three. What I would do is pull these values out of the spreadsheet, and that would be our goal, to match exactly these values. Now we follow the exact parameters from the spreadsheet. It's a square column. So this test data, in a way, it has two purposes. Number one is to use the neutral axis to identify the state for these two axial force and moment values. And then on the output side, we will use them both to compare what we would get afterwards. If we mess something up here, then we will get a different output, but it's all right. What I'm doing is just taking these values. Again, we are trying to validate our extraction, whether it's successful or not, against the spreadsheet. We're not verifying the actual output, the actual values themselves against ACI. That's a totally different verification process, which I would also go to a different video. But again, to reiterate, for this particular video, before making improvements, what I want to do is to validate that our extraction is successful against the spreadsheet. And then any improvement we want after that can come after that. So long as we're confident, we tested, we validated that, okay, we got the exact same capability. So from there, we could do whatever we want. So that's just the purpose of this. All right, what we do is, I'll just run the test script. This is bad, but this is good at the same time. Why? Because we are off for all of the test points, which means there's something wrong with our implementation. So what's happening here? Calculate, blah, 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 neutral axis depth of 8.8, and these are our values. That's the one at the bottom. These is the 8.8 you saw earlier. The negative 792 and 186 are the expected outputs. Both of these. But we don't know. And now what we're getting is this. It's way off. It's way off. This must This must have to do with conversion, perhaps. I didn't, oh yeah, I didn't think about that yet. Let's see. That's what I suspect. Our implementation is wrong in terms of handling internal conversion. It seems we just took the exact implementation without regard to those hard-coded conversion values. For example, from kilonewtons to newtons, like 1000. Maybe it's part of that still, or we forgot to put it in. That's just a critical assumption. Notice I didn't bother checking the individual functions. Remember, there are a bunch of functions here, and from the previous video, I was saying part of the reason why I arranged them in such a functional way is to be able to test them independently and individually. But it seems I'm contradicting that in this, what I'm doing right now, because as you can see, I just jumped straight into the main thing, this function. I jumped straight. I'm not testing each test, but that is because I put it for AI to implement, which is my bad. I didn't, to be honest, I haven't checked it. So you see, you're seeing real time, you're seeing it live, what's going on right here. We are testing just the output, right? And from the results of the test, it's hard to tell where exactly things went wrong. That's a problem, right? It's hard because for us to arrive at the final output, there are plenty of steps. If you remember, we were discussing the steps, which I got rid of them, but there are at least 8 steps there, and the 9th is the optional balance condition. If you recall, just try to remember from the previous video, there are at least 8 steps in there. So we don't know exactly where did we get things wrong in which of those 8 steps, or perhaps all of them. So this is exactly the situation we're trying to avoid. That's why we want to break them down as small as possible, as practically as possible, so that when these things happen, it's easy to test where we went wrong. Or it should perhaps be the other way around, but I've been lazy. I didn't check what the AI did, but the purpose of these unit tests right here is to verify those individual functions such that we can see before we reach this. Because right now we're blind, right? That's what I'm saying. We only have the final output, but we don't know exactly which among the 9 steps we went wrong. And that's the purpose. That's the responsibility of the unit tests that I did not check. I'll check it off screen, each of those steps, if you recall from the previous video, 1 to 8, just 1 to 8, and see where exactly things are going wrong, and then I'll get back and explain what went wrong. All right, so I fixed it off screen, and let me walk you through what happened. First thing is, as I've said, it's on me, my bad. I let AI do the conversion from the VB script to TypeScript. But that's not ultimately bad, because it turns out most of the functions were correctly implemented. And I reckon that's because we split them into smaller chunks, into steps. Remember from the previous implementation part, I did not fully implemented everything, but I broken down each function, each step. And so from there, the AI was able to get a better context of what's happening, because it needed to focus on smaller chunks, smaller pieces of code, rather than the whole thing. So that's good. So the conversion, for example, this one, steel strain, it's straightforward. You just find the ratio between the ultimate concrete strain and just go from there. So it's easier for AI to understand what's going on based from the VB script to this smaller function. Likewise for the still stress. When looking back, when you look at the video again, you might say that this is too much. For example, this one, it's just too. We're just operating on two variables. It's just too much. We could have lumped it into a bigger function, but that's the beauty of what I'm saying here. Since it's smaller, it's easier to handle, whether by AI or by us humans. That's the advantage, and you'll appreciate it also when we go to the unit test. You can test each one, and that's wait, still stress. So this one, so it's also easier to test. So when something goes wrong, you can identify exactly easily where it goes wrong. So going back, that's the first thing that happened. The other one is, oh, by the way, those little functions I'm talking about, they're mostly good because of the reason I just mentioned. But where it went wrong is, surprisingly though, is from one of the assumptions. This is the second thing. It's one of the assumptions. Inside the VBA, I forgot that I included the ACI cap for the axial strength for tied columns, and I had to check the ACI reference to double check that, and it turned out to be this missing 0.8 factor. This was encoded in the spreadsheet that I wasn't able to transfer to the new implementation. And so when I was investigating each function, everything was matching, starting from the stress block, the strains, the stresses, they're all correct. And then when it comes to the the nominal axial force, the output is off. And this is the culprit, the missing 0.8 cap factor. Now, that's the second thing. The third thing is towards calculating the nominal axial strength. This one, I'm still working on this one. I haven't finished this, but there's a missing element here. Specifically, no, it's not shown here, but I separated it into another small function, so it's again easier to manipulate and work with. So I'm still working on it, but the idea is it just sums up everything: the concrete component, the tensile steel component, the compression steel component, and there's this one tiny detail that's missing. It does not subtract the area of the steel, the compression steel, from the concrete compression block. And so the current result is off by a small amount. No, not this one. These are the other tests I was talking about. This one, when it comes to this, I suppose. Yeah, let me put a debugger here so we can see. And that's another one actually, but it's a minor detail, I would say, the conversion factor. These factors are encoded in the old spreadsheet. And that's one of the things we should also work on down the line, is to how to handle that conversion layer. But the idea is it should not, again, following our fundamental principle, the conversion layer should not live inside our core function. We would write something, a piece of small adapter or something to manage the conversion. So going back, I'm just trying to show you through the debugger. This is the thing. This is 199 199. This is in Newton. So if right, so 1991. Take note of the number 1991. And my source from the tests is 1965 something. This one. This is the first. This is the first point from our neutral axis loop. So the neutral axis is 529. The moment is 6.8, and the axial force is 1965. This is now in kilonewtons. So if we go back here, I haven't checked the moment. I stopped here, and then the implementation of the axial force, because, like I said, I missed that 0.8 factor, the one I mentioned before, and now the missing subtraction of the compression steel contribution. So again, it's 1991, and the other one from the test is 1965. I stopped here because I suspect that it has to do with the supposed subtraction of the compression steel component. So this is how it was implemented. You see here in line 118. So it just adds things straight up. But before I proceed, again, I just want to clarify that we're close. You saw the number earlier. It's 1965 versus 1991. So it's just off by around less than 30 kilonewtons. So I reckon that's the additional, compression we took from the whole compression block without subtracting that tiny bit of steel reinforcement right there. So let me check the interface for the compression steel. Resolved steel, should we? Oh yeah, let's take in the resolved steel, why not? So the resolved steel will give us two things, area and the depth. But for this case, we just need the area. I'm just thinking on my feet. I could be wrong, but bear with me. So what we're gonna do here is just straightforward. Let's just return that. See, AI knows what we're doing. Compression block force, we subtract the compression steel area multiplied by compression steel. No. We have the, we need to inject the assumptions here. Yeah? Assumptions. Right. So let's deconstruct. What was that factor? Not the compressive strength, the other one. The 0.8. No, not the 0.8. But should we go back in? Oh, there's too much here. I don't want to exceed. I don't want to go beyond 3 normally. I don't want to go beyond 3 arguments in a function. I just don't like it. Ideally, just do 1 or 2. It's too much, but let's just continue. Yes, concrete, and we want the compressive strength. We could go ahead and we could go straight with pulling the values that we need from these interfaces, from these objects, but I just don't want having too many dots, compression block dot, force dot, but this is all right. So we want the compressive strength and coefficient. Is this enough? I'm not sure. Then what we'll do here is to bring in the net compression, whatever. Then let's call that one. We just implemented. Oh, there's no way around it. We really need to pass the thing. Let me just again do it off screen. But before that, I'm gonna go for lunch. It's like 1, almost 2 o'clock. I'll see you again. All right, so I discovered 3 things here. I tried to go slow because even myself, I'm getting confused. But I discovered 3 things. Number one, the test data is somewhat off. These values, I extracted this from maybe it's a different version of the spreadsheet. I don't remember, but I have another copy here, which I just ran, and you see for the similar values of C of the neutral axis, the results are different. For example, this one, PU and MU, 1995 and 14.9. Whereas from the source, it's different, 1965 and 6.8. And so no wonder I was spinning my head and trying to hit the numbers and inspecting the code where things went wrong. But needless to say, I fixed it now. Let me walk you through. This is the first thing, again, by the way, that I discovered. So let's walk through that. Oops, it's failing. No, I don't mean to run the full test, but I just want to walk through the debugging process. What I was trying to show you is from debugging this, starting at 529, this is how I knew that the output, the test output, or the source for the test output are wrong. So we're starting at 529. We have 9094 something, 94926, and 14947 for the moment. And when we go to the spreadsheet, they're close. Actually, if not 1-to-1, right? And that's 529. If I step through, the next step is 520. And 1962 and 27. 1962, 27. Then I'm going to step another one. 511, 1929, 39, 34. 1929, 39, 44, 34. By point something is forgivable, I suppose. 511.8, the neutral axis. Yeah, that's good enough. So I don't want to go through the rest of this, but the point is, I'm happy to be able to hit the first 4 values here. There's something wrong with the other source. So for us to be able to derive more confidence out of our outputs, I would say just copy this over and replace these. But I'm not gonna do it now. I want to continue with explaining what happened. Okay, so to arrive there, I needed to write the net compression function. So I tried to reduce the signature to just accept the compressive force rather than the whole compressive block object. I realized that's too much. It doesn't need the whole thing. It just needs the actual compressive force right here. And then from there, we would subtract the missing element, which is a contribution of the compression steel. And that's how I was able to fix that. So that's the first thing. Number two is about around the PM function, about the derivation of the capacity point. It's about how we put these functions together. Yeah, I found out that this steel component before, it's taking care of that missing, it's trying to resolve that missing steel element. How I found out is because previously it's asking for the concrete block in one of its signatures. So, sorry, one of its parameters. So the previous function signature includes the concrete block. And I was wondering why why does the steel component need the concrete block? And so I look into that and I realized it was trying to handle the net um, the net compression from here, but it's doing it the wrong way because it should be done on the concrete side, not on the steel side. So that's another source of the problem. So there are a bunch of logic right here previously. See, I deleted them. Displace concrete stress. That one. So I realized, this is the main reason why it's asking for the concrete block object, when in fact it doesn't need it. And so I needed to get rid of that, which I did. And then the signature I altered, removing the concrete block as one of its parameters. And so that did it. That responsibility of this component is just to derive the steel component, which contains the force and the depth, this bunch of stuff. Even the moment, let's question that later on if needed. But this is the idea. It's just packaging the whole uh, steel component with its necessary elements: stress, strain, forces, moments, etc. So that should be its only responsibility. It doesn't need to. It should not touch the resolution of the net compression on the concrete. It should be on the concrete side. So that's another one. And I think I said three. So what's the other one? Nominal axial. Right. The third one is about how we put these things together. Going back to, I think I mentioned this already. This, I needed to add, this if statement right here, just to check the existence of the compression steel. And then as I was doing this, I was questioning why, why did I make the compression steel optional in the first place when, as I mentioned in my previous video, columns always have, nearly always, if not almost always or always, they have symmetrical. Ideally, when you design a column, they should have symmetrical reinforcements, right? So when we have tension steel on one side, we expect the corresponding compression steel on the other side. So that's the most common use case for columns. And so why make the compression steel optional, right? And I was questioning that. And then I realized it's already there. But I think the more compelling reason is later on, I'm already thinking of maybe reusing parts of this when we deal with beams, because for beams, well, it's also another thing is it's rare that you only see one reinforcement. I mean, one set of reinforcement only on one side, but I don't know. I'm going through a rabbit hole of bad abstraction. Maybe we'll see. But that's the reason. That's the reason. I'm just explaining that. And so now, going back to this if statement, just to check whether compression steel is present. If it is, then we would calculate the net compression. And then previously, again, I was passing the whole compression block here because, product of habit, I was passing it on the other function. So why not pass the concrete block again? Then, no, I realized we don't need that. We just need the force. as our basis from where to subtract the effect or the contribution of the compression steel, and then return a new value, assigning it to the concrete force that's defined here at the top. So what's going on here? Initially, the concrete block force is derived from the gross concrete compression, or the concrete compression does not take into account the steel contribution. It's this part. And then that's done, right? Check. And then I'm just assigning the force here because when we step into this check, we would use this as our baseline to subtract the steel contribution. And that's the tiny piece of logic right there. And then once we reach on assembling the concrete component, we will then use either this, the untouched, and let's just say untouched, or the net, gross net. Up, you get it. I mean, I know you get it. That's the idea. And then, so when we get here, those values are already adjusted, already corrected. And so when we put in here the nominal axial strength, it wouldn't be affected. It doesn't need to, again, know any of those things that happen above. And then finally, when we're returning this is where I injected the assumption part of the cap, the axial capacity cap of 0.8 in this example. But why did I put it in the assumption? Maybe because it might change. Maybe next time, or I don't know, sometime in the future, someone will decide that, let's just use the full axial strength and not reduce it by a particular factor. So that's just the reason. So those three main things. Whew, those are mouthful. I guess we can stop here. What I do next is just correct these values and then run it again to make sure that the tests are passing. Okay, so I decided to just continue anyway. It's just a few minutes continuing, so let's do this. I tried to test things around off screen and I found two things. Number one, I could get away with tolerance of 1.5%. Lower than this, the stuff will fail. There's really tight differences right there. For example, this one is good. The axial force of 174.77. But in terms of the moment, there's more differences. Maybe because of the, how the conversion factor changes the scale. We're talking of 1 million conversion factor versus 1,000, from kilonewtons to newtons and kilonewton meters to newton mm. So I think that contributes to it. So 112 versus 113.6. But if let's increase the tolerance to 1.5%, then we can get everything passing. Right, so that's good. So we can see here, it's close enough, right? So this indicates that we are able to extract the capability from the spreadsheet and that we faithfully we implemented it in a different runtime, a different language, different framework, different system altogether. And number two, there's a small caveat. I'm getting a divergence somewhere on these values, and I suppose it has to do with the compression steel, right? So that's a good boundary. We established the limitations of our system, of our extracted system. So at this stage, we can no longer match that of the spreadsheet or those values from the spreadsheet because our system only accounts for compression steel. And once we crosses these values of neutral axis, 61, 52, 44, remember in this particular example, our compression steel is located at 62.5 from the top, from the compression side. So of course, when we break that assumption, that's the module's limitation, right? That's another thing. That's another insight in doing this exercise. We find out and identify the limitations of our model. So this particular converted capability is not capable. What an irony, right? It is not capable of dealing with another layer of tension steel, let's just say. Because at that point, when we cross the neutral axis, our compression steel, our assumed compression steel, would turn into tension if it's still even workable. That way, if we still be able to squeeze a slither of concrete on top of our section to produce the required compression to balance things. But I reckon that wouldn't be possible, right? This is mathematically, it makes sense. But if we go into the engineering implication of this, we don't design for such cases. I don't know, but to me, my personal opinion is that if I have two layers of reinforcement and I'm just relying on the cover, I don't suppose it'll be able to produce such compression. Correct me if I'm wrong. I haven't read specific research around that, but to my intuition, if we go outside the cover, especially outside the spirals, the lateral ties, the concrete outside the lateral ties are the first ones to give give in, right? That's why we have the confinement. So the cover wouldn't, again, I'm just assuming, practically speaking, I wouldn't rely on the cover to produce enough compression to balance the section. So maybe it's fair to say that when we cross a certain threshold of neutral axis, our assumption, our model will fall apart. So we can leave that as a conclusion and as an important limitation of our model, of our capability, that when we cross a particular value of neutral axis, especially as close to the concrete cover, then our model falls apart. This whole thing is no longer applicable. We need a different tool, a different system, a different way of approaching the problem. And that's also a good thing that we uncover from this exercise. So that's it. Let me really end here. I hope you enjoyed this video, and please don't forget to click that like and subscribe button below. And let me know in the comments. Let me know in the comment section. What are your thoughts? What are your questions? What are the next ideas, topics you want to jump into? I'll see you then. Bye-bye.